Welcome to the deep dive. Today, we're really getting into the weeds of numerical
We
analysis.
are. We're looking at some pretty advanced research on the mixed finite element method.
Mixed FEM, right? Applied to these 3D HP2 adaptive curved meshes.
Yeah, that title's a bit dense, I
Yeah.
know. But don't worry, we want to give you the sort of operational takeaway here.
Not just the pure math theory.
Exactly. This is about the engineering side. How do you build computer models that are super fast, stable, and importantly accurate?
Especially when you're dealing with physical stuff like fluid flow or heat transfer inside complicated real-world shapes, curvy shapes.
Right. And we've got sources here showing how these researchers figured out how to solve for two things at once, the potential field and the flux field. Bold symbol.
And they did it with better stability and better precision than you might expect.
So our mission today is really to unpack that methodology, how they
Yeah.
got that high accuracy without, blowing up the computational cost.
And they did this by comparing two different ways of setting up the approximation spaces. Yeah.
Exactly. Two novel configurations. And then showing how efficient they are on, like, big industrial scale 3D problems.
Let's get into it.
Okay, so the basic problem they're tackling is the Poisson equation.
Classic equation, defined by those two linked fields you mentioned. Potential, 2, 1, and flux. Bold symbol. Calculate both together.
And the key choice here, you said, is using mixed FEM, not the maybe more standard approaches.
Right. And the big reason is conservation. It really boils down to that.
How so?
Well, with the standard method, you might get a nice-looking solution mathematically. But when you look closely at how energy or fluid, the flux, bold symbol moves between the little pieces of your
All
model.
mesh elements.
Yeah, the elements. It might not actually be conserved locally. Flow in doesn't always equal flow out for each element.
Right. So if I'm modeling, say, groundwater flow, I need the water going into one computational block to perfectly match what's coming out.
Exactly. Otherwise, the simulation isn't physically reliable. It's just math.
And that's where MixFEM is designed specifically to help. It uses what are called HDiv, conforming finite element spaces for the flux.
HDiv. The div is for divergence.
And these HDiv spaces are built mathematically to guarantee that the calculated fluxes are both accurate and locally conservative.
Wow.
That's the payoff.
Okay, but wait. If you need things to be continuous, like the flux, doesn't that make the math really complicated or maybe unstable? How do you keep it continuous without making the problem huge?
Ah, good question. They stabilize it by being very specific about what needs to be continuous.
Okay.
It's only the normal components of the flux vector that have to be continuous across the element boundaries.
The normal components. So the part of the flow vector pointing directly through the boundary wall.
Precisely. That flow through the wall has to match perfectly between neighbors.
I see.
Meanwhile, the other variable, the potential deb, they actually allow that one to be discontinuous across element boundaries.
Okay. So it's a trade-off.
It's an intentional mathematical trade-off. Continuous normal flux, discontinuous potential. That combination is what gives you both stability and that crucial conservation property. Pretty neat.
Okay, so conservation is handled. But now the geometry. You mentioned real-world shapes.
Right, the headache of geometry. We're not just dealing with nice straight-sided boxes here.
No.
This method is built for complex 3D curved meshes. Think tetrahedra, hexahedra, prisms, but with potentially curved faces and edges.
So if you have an element that's curved, like part of a sphere or something, how do you even do the polynomial math inside that? Seems really hard to standardize.
It would be, yeah, unless you map it.
Map it.
They use a standard technique. Every complex element, let's call it dollar, gets mapped mathematically back to a simple standard reference shape.
Yeah.
The master element.
It's like a perfect cube or a perfect tetrahedron?
Exactly. You use a geometric transformation, technically a diffeomorphism, to sort of stretch and deform your complex element into that simple shape. You do the math on the simple shape.
Where it's easy.
Right. And then you map the results back to the original curved element.
Okay. That makes sense for something like temperature or pressure, a scalar value.
Mm.
But what about flux? That's a vector. It has direction. If you stretch and twist the geometry, the direction gets all messed up, right? You can't just stretch the vector arrows along with it.
No, you absolutely can't. And that's where it gets really interesting. This is a key part. To handle the flux vector correctly across this geometric mapping,
Yeah.
you have to use something called the contravariant Piola transformation.
The Piola transformation, why is that the key here?
Because it's like a mathematical insurance policy. It's designed specifically for transforming vector fields like flux during these geometric mappings.
Okay.
It ensures that when you take your nice conserved flux field from the simple master element and map it back onto the complex curved real element, that crucial HDiv property, the continuity of the normal component, is preserved.
Ah, so it adjusts the vector components correctly during the transformation.
Exactly. It adjusts them so the flow through the boundary remains identical, even when that boundary is curved. It's the trick that makes HDiv methods work robustly on real, complex geometries.
That's elegant. Very clever. And I think I remember reading the shape functions themselves, the basic math building blocks for the flux.
Yeah.
They're categorized based on how they behave at these boundaries.
They are. And this categorization is important for what comes next. They split them into two types.
Okay.
You've got face-type shape functions. These are the ones that are non-zero on the element faces. They handle the communication across boundaries. They ensure that continuity.
Right.
And then you have interior-type shape functions. These guys are zero on all the boundaries. They only affect what's happening inside the element.
So they don't talk to the neighbors?
Nope. They add detail internally, which is useful computationally, as we'll see, but they don't directly influence the continuity across elements.
All right, so we have these building blocks, face functions for continuity, interior functions for internal detail. Now, how do they use these to build the two main space configurations the researchers compared?
Well, the guiding principle is something called the consistency rule. Basically, if you take the divergence of your flux approximation space, you need to land exactly inside your potential approximation space. Build symbol DOL has to equal DDO.
The math has to line up perfectly.
Exactly. So configuration 1 is the standard one. They call it Dimmer-Wöhler, and the notation is typica pianio.
Okay, PQP PT arc. PPPT, if T is the polynomial degree, this looks like both spaces use degree K polynomials in some sense.
Right. And for this standard setup, the accuracy you get for both the flux, bold symbol, and the potential is of order K plus Devloo.
So degree K polynomials give you PK plus Delta-1 order accuracy. That's the established benchmark, the reliable method.
That's your baseline. It corresponds to well-known methods like Raviart-Thomas or TI-RTTs on simple shapes. It's solid. But the real innovation, the clever bit, is in configuration 2, the enhanced setup. They call it MF name, and the notation is PKPK plus $1.
Whoa, okay, PKK plus 1. Let's break that down. The flux space, PK, still looks like it's based on degree calers. So the flux accuracy is still order K plus $0.50.
Still order K plus $7.
But the potential space is PK plus $1. That looks like it uses polynomials 1 degree higher. Does that mean?
Exactly. It means the potential accuracy gets boosted to order K plus $22.
Wow, so you get an extra order of accuracy, like an extra decimal place of precision for the potential field.
That's the core idea. And the really interesting question is how they achieve that higher accuracy for Wöhler without seemingly increasing the complexity or the cost related to the border fluxes.
Yeah, that sounds almost too good to be true. Usually higher accuracy means more computation, bigger systems to solve.
Well, they pulled off a really neat trick. Remember those interior type shape functions?
Yeah.
The ones that live only inside the element.
Uh-huh. The ones that are 0 on the boundaries.
They achieved that K plus 22 accuracy boost for the potential dollar by basically stuffing the flux space with more of those internal shape functions. Specifically internal functions whose divergence lives in that higher PK plus 1 space.
Ah, I see. So they increase the richness, the degrees of freedom inside the element where it's computationally cheaper, in a sense, we'll get to.
Precisely.
But they kept the face type functions, the ones that determine the connections between elements and the size of the final global problem. They kept those fixed at degree dollars.
You got it. The complexity you pay for globally, which is tied to those face functions, stays the same as the standard PK-DOL method.
Yeah.
But the internal representation gets much richer.
It's like building much more elaborate internal scaffolding inside each element.
That's a great analogy. Stronger internal scaffolding, which gives you a better final measurement for the potential dollar. But because that scaffolding is designed to be removed before the final assembly,
the global cost doesn't go up. Clever.
Which brings us neatly to the removal process, static condensation, or SC.
Right. If you have all these extra internal details, these extra degrees of freedom, you need an efficient way to get rid of them. Otherwise, that free accuracy isn't free at all.
Exactly. Static condensation is the key optimization technique here.
Yeah.
You take all your degrees of freedom, your DoFs, the flux has internal ones, bold symbol, and ones associated with the edges or faces. The potential also has some internal ones and maybe one average value.
And the goal of SC is to eliminate the internal ones.
Yes. You eliminate the purely internal flux DoFs, bold symbols, You basically solve for them locally on each element, expressing them in terms of the face edge DoFs.
You figure out their values based only on what's happening at the boundaries of that single element.
Right, and then you substitute them out of the equations.
Yep.
You effectively condense them out.
Leaving you with
A much, much smaller global system of equations that only involves the degrees of freedom associated with the element boundaries, the edge fluxes, and that single potential value.
So the big advantage is the size of the final matrix problem you need to solve globally is drastically reduced.
Hugely reduced. Its size is proportional only to those border fluxes, the face edge DoFs.
And here's the crucial link back to the two configurations. Even though that enhanced PK+1 method uses more internal functions.
Right, it has a richer internal space.
The number of border functions, the face edge DoFs, is the same as in the standard PK dollar method for the same degree dollars.
Exactly. Which means the size of the final condensed global matrix you solve is identical for both methods.
Wow. So you get that higher K plus 22 accuracy for the potential dollars for the exact same final computational cost in terms of solving the big global system.
Yeah, that's the magic of it.
And the numbers they reported for how much they could condense are really impressive. I think for a polynomial degree, K10 it all.
Yeah, using hexahedral elements, the PK+1 setup achieved 92% condensation.
92%, meaning they mathematically eliminated 92% of the original degrees of freedom before they even started solving the main problem.
It's massive. And interestingly, the pitot configuration actually condenses better than people.
Why is that?
Because it deliberately includes more internal shape functions relative to the border functions. So the ratio of stuff you can eliminate to stuff you have to keep is higher. More internal scaffolding makes the demolition more effective, percentage-wise.
Okay, that makes sense. And this efficiency gain from static condensation is then combined with another strategy, hp-refinement adaptivity.
Right. hp-refinement adaptivity is like the smart targeting system for your computational effort.
Dollars being the mesh size, pico being the polynomial degree.
Exactly. Instead of using tiny elements everywhere or a very high polynomial degree everywhere, which would be incredibly expensive, you adapt.
You refine selectively.
You refine the mesh size only in regions where the solution is changing rapidly. And you increase the polynomial degree only in regions where the solution is smooth but needs high accuracy or near singularities where high degrees work well.
So you focus the computational power exactly where the physics demands it.
It's surgical precision for your simulation, essential for problems with sharp gradients or tricky spots.
So to see this whole system, the mixed FEM, the Piola transform, the enhanced spaces, static condensation, HP adaptivity all working together, the researchers tested it on a really relevant industrial problem.
Yeah, classic one. Simulating fluid flow in a porous medium, like an oil reservoir. It's a big challenge in petroleum engineering.
Okay, so in this context, what are our variables, TUDA and bold symbol faith?
Good question. Here, TUDA represents the fluid pressure field in the rock.
Right.
And bold symbol is the Darcy velocity, basically, how fast the fluid is flowing through the porous rock. And the dollars in the equations represents the rock's properties, its permeability.
And the specific problem they modeled was flow around a horizontal well.
A cylindrical horizontal well. Yeah, inside an elliptical drainage area. So complex geometry again.
And I bet near the well itself, especially maybe at the ends of the horizontal section, the pressure changes really fast.
Absolutely. You expect singularities, sharp gradients in the flow near the toe and heel of the well. That's where the fluid is entering the wellbore.
Perfect place for HP adaptivity then.
Exactly. They used an HP adaptive mesh, keeping the curved geometry of the well and reservoir, and they specifically cranked up the polynomial degree only in the elements very close to that toe and heel.
So they didn't waste computation using high degrees out in the far field where the flow is smooth.
Precisely. Targeted refinement.
Okay, so the bottom line. When they put it all together, the better spaces, the static condensation, running it in parallel on multiple processors, how much faster was it? What was the real-world impact?
The impact was dramatic. They ran a specific test case, fairly complex, and the combined effect of using static condensation and parallel processing reduced the total computation time, the CPU time, down to only about 8% of what it would have taken without those techniques.
Wow, 8%. That's more than a 10x speedup.
It's a massive gain. It really shows how these numerical methods move from theory to making previously infeasible industrial scale simulations practical. #outro.
Okay, this has been quite a deep dive, appropriately named. We've seen why HDiv conforming spaces are vital for conservation.
Especially for flux.
Understood how the Piola transformation is crucial for making these work on realistic curved geometry.
Preserving that flux continuity.
And we compared those two configurations, seeing how the enhanced PK plus 1 gives superior accuracy for the potential variable $1.
Yeah, that K plus 2 accuracy boost.
All while keeping the final computational cost, thanks to static condensation, roughly the same as the standard method.
Right. And connecting that to the bigger picture, these kinds of advances really do change the game for modeling complex 3D systems. Think reservoir simulation, but also potentially other fields.
Definitely. The ability to get more accurate potential or pressure data almost for free computationally is significant.
It is.
And actually, that specific point, that the P configuration improves accuracy for potential, but not for the flux, which stays at K plus $1. That brings up a final thought for you, the listener, to maybe ponder.
Oh, interesting.
We saw this method is great for pressure or potential data. So thinking beyond just fluid flow, what kinds of other physical or engineering problems out there might specifically demand highly precise potential or pressure information, maybe even more so than needing super precise flux or velocity data?
Yeah, where would that specific trade-off, that targeted accuracy boost for most valuable? Makes you think about different physics problems.
Exactly. Where does that particular enhancement really pay off? Something to mull over.
And just as a final note, for anyone interested in the practical side, this work was actually implemented in a real software library called NeoPZ.
Right. So these aren't just theoretical ideas. They're being built into computational tools.
Exactly.
Well, thanks for joining us for the deep dive. We hope you found this exploration useful.
Yeah, thanks everyone.
We'll see you next time.